Welcome to Lesson 24, Analytical Method Development. In this lesson, we will be talking about what is analytical method development, what tests need analytical methods validated for, and what are the parameters to be validated. So what is the purpose of analytical method validation? Analytical method validation provides documented, objective evidence that a method measures what it's intended to measure with acceptable performance parameters such as bias and precision. The regulatory requirements obviously require methods validation to be performed, and you'll see it in the US FDA. It's also in the European regulations, the UDRLEX, and there's an ICH Q2 guideline. The ICH validation of analytical procedures, text and methodology Q2 is attached to your appendix for this lesson, and you can see the link for it here. The US Pharmacopoeia has also published specific guidelines for method validation for compound evaluation too. The analytical method life cycle. So number one, the analytical method development to optimize a method for its intended use is defined. Second thing that happens is it's qualified. So to prove the method has the ability to perform for its intended use, and the initial documentation is completed. The method is then transferred to quality control, and here the method transfer to the end user or the clients. Method validation occurs at this point to prove that the method has the ability to perform for its intended use, and the documentation needs to be completed for that. And then periodically it's monitored and reviewed to make sure that it is maintaining competency. And methods may be revalidated if there's any change to the method performance changes over time. Analytical methods which must be validated. All tests that determine the quality of the product, either directly or indirectly, must be validated. If a pharmacopoeia method is used, a full complete validation is not required, as there is a lot of data already in relation to this test. Examples of analytical methods for API. So visual inspection and identity, they are qualitative results. Physical measurements like length, etc. Carl Fisher to check water content, pH, titrations. Loss and drying method for determining water and or solvent content. And HPLC methods for measuring product purity and impurities. This is not an exhaustive list, rather to give you an example of some of the types of examples of analytical methods. Validation of analytical method is completely different to a validation for a process. The supplier ensures that the instrument is installing and operating correctly. The site, i.e. the quality control lab, is concerned with the performance qualification. So the parameters that we need to validate as part of a method validation are precision, accuracy, limit of detection, limit of quantification, specificity, linearity, range, and robustness. Accuracy and precision are two terms that people often find quite difficult to differentiate between. In this diagram, you'll see that we are very accurate and very precise. So the accuracy means that we hit the bullseye. The preciseness means that all of our targets are close together. In this one, we are inaccurate. We didn't hit the blue eye. And we are also imprecise because our results are scattered all around the target. Here we are accurate, we didn't hit the bullseye, but we are very precise because all of our results are targeted together, so they're all close together, which means it's very precise. And in this one, we are accurate because we're hitting in and around the blue bullseye, but we are imprecise because our results are not all targeted together. So the accuracy is the degree of agreement of a test result with the true value. So again, you can see we've got accurate and precise here in our diagram. The samples for this test need to be prepared using materials of known purity, so we'd be looking to use reference standards that are certified or spiked placebos. The accuracy should be established across the specified range of the analytical procedure. Note it's acceptable to use a spiked placebo where a known quantity or concentration of a reference material is used. Precision, the degree of agreement among individual results. So we're interested here in three different components. We've got our repeatability. So a procedure is applied to a number of identical samples. So that's intravariability. So can we produce the same result if we keep using the same sample? Intermediate precision then, if we do this test on different days with different analysts using different equipment, is it still going to be as precise? So that's intermediate precision. And then reproducibility can be between labs. Is this procedure robust enough to work between different labs on different days with different people operating it? Repeatability is measured by the scatter of individual results from the mean, and it's expressed as the relative standard deviation, the RSD. So the RSD is equal to the standard deviation divided by the mean. And you'll remember from our diagrams earlier, our accurate and imprecise, and are accurate and precise. So precise means that they're targeted and there's a good degree of agreement between individual results. Linearity. Linearity indicates the ability to produce results that are directly proportional to the concentration of the analyte in the samples. So a series of samples would be prepared in which the analyte concentrations span the required range. If there's a linear relationship, the test results should be evaluated by appropriate statistical methods. So you would be using a minimum of 5 concentrations. The calibration curve. It is the relationship between known concentrations and experimental response values. The goal is to determine the unknown concentration of a sample. So if we've got our linear line here, we can hypothetically say, if our regression is good enough, that a result along this line here should give us this concentration down here. So you remember from before when we talked about our Gaussian curve, we want to see a sharp peak. That means that we have got good agreeability between our results and a small standard deviation, and that's a good response. If the wider this peak is and the more uneven this peak, the less our linear regression is effective, so the less accurate our response is. This is a typical plot for linearity. Our table here is given our results. So what we're plotting on our y-axis, we're plotting the material that we weighed out, our reference material, and on the x-axis we're plotting the results that we received from our instrument. Our green lines here give us a 95% interval for our results, and we've calculated what our intercept is, our limit of linearity and range, the slope of our line, and our correlation coefficient. The calibration curve should be prepared in the same biological matrix, so if you're using plasma, buffers, solvent, water, whatever you're using, as the sample. And the calibration standards and the quality control samples have to be authenticated. Analytical reference standards should be prepared separately in a solution of known concentration or using certified reference standards. So, reference standards. A reference standard is a traceable raw material standard. It's usually in a crystallized form that you dissolve and volumetrically dilute to make your working standard. Then the working standard is what you use to do your work. Where it's specified in an official USP compendial monograph, a certified primary standard must be used, and they can be ordered through the USP. Just to give you an example of that, if you are performing a HPLC purity and degradation assay on an aspirin tablet, for example, the client would send you your reference standard, or you could buy it from the US Pharmacopoeia as it's a standard material. And it would come with a lot number, a purity coefficient, an expiration date, and a sort of other things like its storage requirements. So that information makes it traceable and it's recorded in the preparation notebook. Then, as per the assay method, the working standard would be dissolved in your volumetric flask and diluted up to volume. You might need to make subsequent dilutions then if that was necessary, and that would give you your working standard. Your working standard is used to make your calibration curve, so you would be injecting those samples into the HPLC and you would be determining the amount of aspirin tablets that were being analysed. The range is an expression of the lowest and the highest levels of analyte that have been demonstrated to give linear, accurate and precise results for the method. And you can see in this example here, so we've got our amount and we've got our response, and our intercept is here. We've got our LOD and our LOQ, but what we're interested for range is this part of the graph where we've got a linear range. Once it's sloping off, we're no longer in a linear range. Specified range is normally derived from your linearity studies. LOD, limit of detection. LOD is the smallest quantity of analyte that can be detected, but not necessarily determined in a quantitative fashion. So ways that you can do that is by visual evaluation. So where you've got analysis of a sample with known concentrations of analyte, and by establishing the minimum level at which the analyte can be reliably detected. Signal to noise ratio you can do as well, so where you compare the measured signal from samples with no known concentrations of analyte with those of blank samples, and establishing the minimum concentration at which the analyte can be reliably detected. So we're looking for a signal to noise ratio between 2 or 2 to 1 in order for that method to be valid. We can also use the calibration curve using statistical tools, so we're going to be having a look at these in a minute. There's also other methods that you can use to quantify your limit of detection, and if you look at the ICH Q2 guidelines, they give you a lot of good information on that. LOQ is your limit of quantification, so that's the smallest quantity of an analyte that can be detected and quantified. So approaches include your visual evaluation again, determined by the analysis of your samples with known concentrations of analyte and by establishing the minimum level at which the analyte can be quantified with acceptable accuracy and precision. The signal to noise ratio, again looking at your signal to noise in comparison with a blank sample, this time you need to have a typical signal to noise ratio of 10 to 1. Again, you can use your calibration curve and statistical methods to calculate your LOQ. We're going to have a look at that in a second. And there are other methods as well as outlined in the ICH Q2 guidelines. There are 3 main analytical areas you would be concerned with when you're talking about a validation of a method. The first area is area 1, where you can't detect any analyte. Area 2, where you can detect that there is analyte, but there's not enough for you to quantify it, and level 3, where you can quantify the amount of analyte that's in your sample. What is signal to noise ratio? So noise is measured by running the instrument with a blank sample. The ripple generated is the noise due to the instrument's electronics, the mobile phase, etc. The peak is measured relative to this noise and the ratio is calculated. So that is known as your signal to noise ratio. So here you can see this is our baseline, that is our noise underneath here, and then we've got 2 peaks identifiable. So limit of detection using signal to noise ratio. For LOD, your signal to noise ratio has to be greater than 2 to 1. So this is our signal to noise ratio. That tells us that we have an analyte. It's not big enough to be able to tell us how much it is. Peak A is acceptable for LOD, limit of detection, but not for LOQ. We can't quantify it. It's too small. For limit of quantification using signal to noise, LOQ of 10 to 1 or above ratio is needed between the baseline and the peak. So for this one here, we've got greater than 10. So we're able to quantify the amount of sample that's in this peak using some analysis. Another method you can do is to use a calibration curve. When you've drawn up your calibration curve, you can use the following equation. Your LOD can be calculated at 3.3 times the standard deviation divided by your slope, and your LOQ is 10 times the standard deviation divided by your slope. Specificity, selectivity, is the ability to measure unequivocally the desired analyte in the presence of components such as excipients and impurities that may also be expected to be present. So can your test be selective enough to pick out the analyte that you're looking for in the midst of everything else that's in the sample? An investigation of specificity should be conducted during the validation of identification tests, the determination of impurities and assay tests also. Identification, determination of impurities and assay testing must be specific. The bottom 2 plots show a HPLC analysis of pure and impure samples. So the chromatographic signal doesn't indicate any impurity in either peak because they're eluting too close together. So when you look at the spectral evaluation, you can see the breakdown. So one peak is pure. This one has an impurity match because you can see there are 2 different things eluting at the same retention time. And this one here is a pure peak, so the purity match is 999. Robustness equals to reproducibility. So robustness should be considered during the development of the test method. It shows reliability of analysis with regard to deliberate variations in parameters. So we're looking at things like sample preparation time, the stability of your analytical solutions, how long can they last for, if things are exposed to heat, light, humidity, over time and age, what happens to them, will they degrade, the experience of the analyst, will different analysts be able to achieve the same results regardless of their abilities, if there's slight changes to test methods, how robust is your method going to remain. System suitability is important. It's important to check to confirm that the test method has been set up correctly. It should be verified during your method validation. A system suitability test would always be run before a test and also at approved intervals thereafter. An example, we will run a standard solution and confirm the results are consistent with a reference. Tailing factor allows for higher sample load, and resolution allows for method variation and for column aging. The RSD of replicate injections checks our system performance to make sure it's operating at its best. So just a quick review. Linearity uses standard solutions with varying concentrations of analyte. Precision uses identical solutions prepared from separate identical samples of the same batch of homogeneous material. And accuracy is established from linearity studies where the samples were made up from a reference material where the concentrations of analyte are known. There is a little bit of reading for you here. It's referenced in the appendix to this lesson, so you can have a look at it. Over to you. When is analytical method performed? What is the difference between precision and accuracy? How would you calculate LOQ and LOD? Thank you very much for your time and attention. We'll see you for the next one.